perspective. However, the main themes that I'm going to cover will be applicable widely outside of robotics, right? The main thing I'm going to harp on here is wanting the ability to say something about your code, just to say anything about it. Can you say what it does? Can you say what it doesn't do? These are really useful things to be able to talk about code, okay? If somebody gives you some component off the shelf and said, it will crunch your data, if it solves your problem, then you're done. You can get on with your life. If it doesn't, you have nothing, right? You can't compose a larger system out of it. And one of the best tools, perhaps the best tools we have for talking about our code are types. Types are going to be used to classify the things that our programs take as inputs and they offer as outputs. Types are not, they're going to be used to give assurances that let us build a foundation on these components. And they're also going to be a propulsive force that is going to pull our code at runtime in directions that you might not have thought it could go. So, functional programming, static types, they've hit the mainstream, so I don't need to convince anyone here of their value. But I'm going to take a sort of antagonistic viewpoint for a while in order to motivate some of the discussion. So, you ask a lot of people, well, why don't you like types? Using types, it's like wearing a straitjacket. They put handcuffs on you. They restrict my range of motion. I get boxed in and I can't move. There's a real sartorial theme to this, which we could investigate a little bit more because it's actually kind of interesting. So here's Donnie on bowling night, and he's very comfortably dressed. He's dressed suitably such that his people he's bowling with are comfortable with his attire. He has a nice range of motion. He's able to bowl very nicely. If he were doing other things, he might want other accessories or other wardrobe choices. He might want steel-toed boots or a hard hat or protective eyewear or one of those boxes with rubber gloves so you can handle radioactive things inside, okay? For right now, he's just dressed for going bowling. But we can take Steve Buscemi and look at him in another role, and he's dressed completely differently. And this offers us a great opportunity to question our perspective. And that programmer is saying that types feel like a straitjacket. You have to ask, who's wearing the straitjacket? If I'm a guard transporting the dangerous criminal, then restricting the dangerous criminal might be good for getting this job done. Okay, why? Because that person is going to act unpredictably. I don't know what they're going to do next, and they might be a danger to themselves or to others. Now, a lazy guard could say, it would be far more convenient if the prisoner I was transporting had no restraints. So I could say, Steve, hold the door open while I transport this tray of cookies, But that would be a bad trade-off. Now, is this hyperbolic? It's not hyperbolic, it's dramatic. Because the reality is pretty much just as dire. If you're a roboticist in particular, you have wonderfully tangible manifestations of your code, okay? If you're programming something that is wielding a dangerous weapon, maybe the code that's driving that thing should have a straitjacket on. And is my dealing with that code made more difficult because it's being restrained in some way? Maybe, but it's worth it. I don't want that thing to be free and just hope everything goes well. Even if you're not dealing with weapons or anything dangerous physically like that, surveillance, security, we have social responsibilities that are attached to our code, and we need to live up to all of that. So maybe somebody is going to say, well, fine, types have positive advantages, but in order to use them, I need to get real ticky-tacky. I need to make sure every I is dotted, every T is crossed. And you know what? I've written a lot of programs where I haven't done that, and they've worked, so what's the point? I don't want to write down every little detail, and if I did, that would end up being most of my time. And so as a roboticist, we see situations like this a lot too. So my colleague Ben Cohen and I are modifying a project, and we want to add more capabilities onto it. You can imagine all the data streams that we have when we're working on this. So there's the vision processing, there's the planning, and then we added the shelf over the conveyor belt. So we're doing the object recognition and the pose estimation and the planning for the arms, and it picks up the object and then it needs to get it onto the shelf. So as we're adding these things, we keep on adding new data streams to the stuff we want to log. So we don't have any sensors on the shelf, for instance, but maybe we would like some because we can't do it quite perfectly yet. And this just is another example of, yeah, the types are okay, but they're just there to get under your feet, and you're going to step on them and you're going to fall over. So let's make this really concrete. This is the prestige data set from R. It's used in a lot of examples. It's a comma-separated value file. The data is okay, I guess. It's kind of annoying that the header row that gives you column names seems to be missing an entry right at the beginning of what might be a crucial one. You could have other questions like who's choosing these abbreviations for some of these things, and aren't these quotation marks superfluous? So what is the wardrobe choice that's made when you're dealing with this data? Well, as it's usually practiced, the wardrobe choice is exactly what you would expect, okay? But this is not a functional wardrobe choice. This is a wardrobe choice chosen for superficial reasons. And we want to add some functionality to it. That data was not perfect. So let's not get our nice shoes dirty. Let's get some rubber boots, some Wellingtons, maybe some traction so that we don't sink down into the data that we have. And good news is it's not hard to do. It turns out that that data did have types, and they're not hard to find. So this is an entire Haskell program. It's 3 lines. We have a language pragmas. We have an import of the frames library. And we have a line that says, give me a type called row and infer everything about it from that data set that I had. So I didn't need to now duplicate information. That data set has a lot of information. Even if it might have been messy, there were column names, there were evidently data types, there were quoted things, there were numbers. And rewriting that in my code would be a bit of a nuisance, in particular when somebody hands me a slightly different CSV file, and now I need to duplicate that effort. If we're in Emacs, we load this into the REPL, and we can say, well, what is this row thing that you've now given me? And it is a record. So this is building on John Sterling's vinyl records libraries. It's a wonderful library. A way of thinking about this is that this rec type is like a list, so you can cons elements onto the ends, but it's also like a tuple, in that each element can have a distinct type. Now this has been adapted for dealing with CSV data. You have these names and an arrow and then a type. Those names and arrows exist only at compile time. So now the type checker can say, aha, I know exactly what index to look into to pull out any of the values. So they're going to be erased. They're not going to be there at runtime. But they are giving us a bunch of unique types, which is what gives us the computed offsets when we index into one of these records. So a record here is a product of all of these things. What are the types of these things? Is it a text? Is it a double? No, that's not saying enough. Because how did I infer these types? There must have been some set of types that were candidates that I could infer. And that's going to define a universe. Each of these types is a member of that universe. So we don't just have education as a double. We have education as a double that could have been an int or a text, or in this case a bool, or maybe a date, or any other data type that you can parse from text. So let's work that idea a little bit more. Normally we would define a data type and we'd have variants. And we'd say we have a data constructor that's going to act as a tag for what is the actual payload that we're carrying here. But what if rather than having tags, we just moved all that information over into the type? So now we're not going to have a record, we're going to have a co-record. Where a record is a product, a co-record is going to be more like a sum. A sum is going to look like that top data type that you'll be more familiar with, that style of declaration. But you can see there's a lot of similar information here, in that we have 3 possible choices, except that all your set of choices is now captured all at once in the type of any value whose type is t. And so this is what it looks like in Haskell. So we can define the data type. It just has one constructor, and it takes one payload field. We have this extra context called f. It's usually going to have a functor constraint on it, hence the name f. But we can use that to provide anything that's missing. We can use that to capture effects. We can use that to now play the role of a data type tag. That is how we do the discriminated unions. But I think this example is kind of neat. So we've defined a type alias, and now we've said I have a smart constructor, and all that's doing is I want to be able to print these at the end of the day. So I'm going to capture up a show dictionary, which is how Haskell prints things. So this actually becomes more like an identity functor where every element has a show constraint on it. So I've applied a constraint to everything that's in t's. Now I can apply my smart constructor call to a little character and say, that's an element of t, right? And GHC will say, yes. Here's unit. That's an element of t too. Yeah, that's an element of t. Boolean, that's also an element of t. So now I have these things that are going to be little values, individual values in the row, and their types are not just Boolean, character, or unit. They are Boolean, character, unit from this universe. So there's a relationship amongst their peers, as it were. If we try to put something that's not on the list in, we get a type error. It's not the prettiest type error, admittedly, but it says that integer is not an element of the empty list. We can agree with that. But the point is, whenever you see an error saying something's not an element of the empty list, it was not in your set. So what do we do with these things that we have a column that's an element of a sum type, is that we can now flip them into a record type where every element in the record is a maybe. because the sum said you had a choice of one of these three things. And the record is going to have all of those three things, except all of them is going to be wrapped in an optional kind of construction. Now, that means that we could promote them and go between them. So if I have a co-record with a little character in it, I can say, give me the full record that has the same universe, but what fields are going to be present in that record. And that's why we have that maybe wrapping each of them. So the record has three fields. The first one is just A, and the last two are both nothing. And we can do that for each of the possible types in our universe. And we can look at them all together to see just what's happening. So we really do have different values, but they're connected by these type lists that are happening. This is going to be really important because this is how we do parsing and how we do the inference from the data. So each of these, so we have a universe that the user is going to supply. We have a default universe. But if you want to create your own data type that's parsable, it'd be great if you could just pull that straight out of a CSV file that also has ints and doubles and bools, right? But you have your custom data type. So you can create your own universe, and from that, we can try to parse all of these little co-records. We can promote them into records that are sparsely populated by things we were able to parse. And then we can go through that record that's sparsely populated and decide which one we're going to pick out of it. There might be none. The record's interesting. The record could be all nothings. So when we pull a co-record back out, we might fail. It might be nothing. If there's more than one value, we have to pick the first or the last or obvious choices. For doing the parsing for these CSV files, I order my types in a way that works, that picking the first one is going to be the sort of smallest type that can represent the data that I have. So this is all very interesting, but it seems hard to believe in some ways, but it's not. So this is now a full program that is going to use the chart library by Tim Docker, where we create a row type, we load in the file, and this is now doing something nice with loading. We do this in-core array of structures. So we've done all this type inference, and so how do you store this data if you want to load it into RAM? It's going to be a column-based store where every column has a distinct storage strategy based on the type of data that's going into it. If you have small data, we can pack it really densely. But the API we present is a normal one where you index out rows. So your data is crunched down as small as possible into unboxed, packed arrays, wherever that can be done. But the indexing and the API is perfectly natural, row-based. We can also, and you'll see later, do this in a completely streaming fashion. So if your data set is far larger than your RAM, then streaming is no problem, and all the same functions you write are going to work. We usually suffer in Haskell in that we don't have things like matplotlib or ggplot2, but things are getting better. This doesn't look terrible. I mean, if you don't know Haskell, I'm sure it does. If you do know Haskell, then it looks a little bit imperative, but it turns out that works out pretty well for setting up plots. Anybody who's set up a really fancy plot using any of the modern tools has had this experience. We're like, darn, those results are really nice. I don't care if it was, I'm not proud of what I wrote, but the results are nice. And it's okay, because these plots are pretty ad hoc, right? You're often tweaking things and moving something around, so they're perhaps not library components themselves. So this is in Emacs, and you can see I put this little bit down at the bottom, looks like a comment. In Emacs, I can, of course, view my code as an org file, and that can display my images in line. So I can take my code, load it into the REPL in Emacs, that generates my plot figure, and then my view of the code as org can pick it up and show the plot in line. And so in Emacs, you can also do formatting. This is getting a little low on the screen, but I had some bold-faced stuff. You can do links within a document or between to other documents. And get another look at this. There's lots of great facilities there. I love Emacs, but this is not a talk on Emacs. If you want to do autocomplete of everything, type holes, case splitting, Emacs has all of those IDE features if you're willing to get yourself set up. But a lot of people aren't willing to go through that process of getting themselves set up. But there's really good news. It's not a real command. I'm sorry, I made that up. You looked so concerned. So Andrew Gibionski has done tremendous work at putting together iHaskell. This is built on the IPython tooling, which gives you a notebook interface that can be run at a console or through a web browser. So a notebook interface is really handy, particularly for people who don't see themselves primarily as programmers. It has advantages in that it's a very rich presentation. You have code, formatted text, equations, plots and images, and they're all kind of intermingled. Another advantage that it has is it tries to support some notion of persistence. So a problem when you're exploring a data set is you might take 10 seconds to load some data off disk into RAM, and you want to test out different queries on it. You don't want to have to reload that 10 seconds every time you change your code one little bit. So that bit of persistence is very helpful. This is just to show that this is running in a browser. And this is referring to CJ East, who has done a lot of really cool work over the past literally week or so of integrating this frames library with iHaskell. So I'm going to look at it a little more closely. iHaskell offers a sort of strange interface if you're used to writing Haskell, because you have imports, but then look, then you bind, get frame gets binded to OM. So this is like you're working at the REPL, and you are. But then you can just add more imports anywhere. And when you say something like down at the bottom, display chart, a wonderful thing happens because you're in a web browser and it displays a chart. So this is a nice graphical way of using these tools and doing data exploration. It is still Haskell. So I took some liberties with CJ's code to write them more the way I would write them, because I think this demonstrates another key feature of frames that is easy to miss. One of the complaints that you have about static typing often is that you get boxed in. It's too rigid. You've committed to a schema ahead of time, and now you can't adapt when your data changes. And I started off by saying my data is always changing. I'm always getting new columns, a new sensor from a robot. So let's live up to this. What is the type of this edu income? I wanted it to take a record and give me a pair of doubles, because that's what's going to get plotted as points. And I asked for the type, and oh god, it scrolls off the screen. So I couldn't take a screenshot very easily, so I scrolled it over and took another screenshot. And you know, this is frightening. If you look all the way down to the right, that's all that matters. It says rec R0 arrow double comma C. That C should be a double for the way we're going to be using this thing for making a plot. But thankfully, there already is a way that you would write it, and I usually write type signatures myself, so I'm not looking at the inferred types as much. This is how I would write that type, and we can verify that it does, in fact, type check at it. This is now saying there's a record that has some fields R's, and income is an element of R's, and education is an element of R's, and under those constraints, I can give you a pair of doubles. So what's great about this? If columns get moved around, this code still works. If you add columns, it still works. You remove columns, it still works. And it always works optimally, because it always gets compiled to the data it's going to run against, right? Because the type checker has access to the schema of the data you're applying it to. So you wrote this code for one data set, then someone gave you a data set and they've moved things all around, you recompile, and you have perfectly optimal code. So you're getting, you know, full speed GHC with unpacked numerics. You have you have streaming representations that are going to run in constant memory. And if you can load all your data into RAM, you're getting extremely efficient storage due to the distinct storage decisions made on a per column basis. Just as another example, this is Frames is a library that's on GitHub. You can go look at it. There's a tutorial that'll be much better than I'm doing here at walking you through it. But this is just showing off iHaskell, because I think it's neat the way that you could do development like this. And so I broke it up more into cells. And I said, well, here's another data set that has various blood test results. And if I loaded them in GHCI, I would ask for the info about this type. I:, Trigley is the type name I gave it. And it responds interactively. It pops up a little window. This looks weird. They're all ints. So that's a little bit concerning. We might want to double check our data. We're in a browser, so we can convert to HTML and say, oh, those are all ints. And those column headers are very inscrutable unless you're a doctor. But we'll trust that they're accurate. But you see, this is getting a nice way of taking a tour through the data and zeroing in on the functionality we want, but we've not left Haskell. So all the goodness that you have of writing fast numerical code, of writing things with nice levels of abstraction, it's all still right there at your fingertips. This is now going to do a kernel density estimate using the statistics package. It doesn't matter. I'm doing this entirely to lead to a punchline in the form of a plot. This is more usage of chart. This is now more complicated. This is taking a curve and saying fill the area under the curve. I got that from their example program. My plots, I wanted to have sort of thick outlines as well as the fill color. And again, I just end it with display chart. And it displays something that looks just as nice as you get from the more venerable numerical analysis tools that we have out there. So this is a real opportunity for Haskell to sort of move more into an area where it's been not super well represented for want of tooling. And CJ and I are working on how melt is going to work if you used R, how melt will work for these records, so you can deform them and reshuffle columns around. And I have a strong suspicion it's going to work with no overhead at runtime, but we haven't done that yet. I would love it if more people got involved, because before we start setting things in stone, it's nice for someone to come along and say, this piece of the API has to be there, and if we're missing it, then we'd like to fill that in. Okay, so that was business suits. So we've talked about types that are somehow impacting us as programmers, and types that are impacting the systems that we are programming. What are today's types doing? Or is it really straitjackets? Are we really boxed in? Let's not be so grandiose, right? Our types are offering us a modicum of modesty. And this would be shocking, I think, to people from other realms who aren't familiar with quite how loose we do things, and then we call ourselves engineers. But you show engineers these signs, and they immediately start thinking of loopholes and how they could get away without having to do any of these things. But this is a mistake. Don't be lazy, because we have opportunities to do lots of wonderful things. You could use Coq, you could use Idris, you could use Agda. This is Liam O'Connor's Agda sign. I don't know what it is. So my guess was that it was meant to be this. You could be wearing this. Now, we don't wear these to work very often because our colleagues will look at us funny. But these are extremely functional costumes, I've been told. I'm not an expert. So our colleagues will be more comfortable if our choices are perhaps more prosaic and practical and functional. That doesn't mean that we have to limit ourselves to being boring, though, right? So we can bring our own style onto things. And the point here is that we have a hard hat, but not just any hard hat, okay? This is going to be an amazing hard hat. All right. So we're selecting pieces of clothes that are suitable for whatever we're going to do. And now we want to be able to talk about it in more specific terms. And the way that we usually do this in Haskell, and the way we've done it in Lisp for a long time, is using a domain-specific language. We like domain-specific languages because by shrinking the domain of discourse, terms become less ambiguous, and we can rule out certain classes of problems whose causes are no longer expressible, which is huge for us as proponents of static types, right? We want to don't make the error state representable. I mean, now you've eliminated all your problems. There's a downside that a lot of people view, which is that you're using the EDSL because your language you're using and its compiler and its runtime aren't very good. So I couldn't run the real-time system, so I have to generate code for somebody else. It's kind of the escape hatch view of things. And it's made worse when you say, well, let me just simulate my EDSL, and you're paying this huge overhead penalty because there's some interpretation overhead. And so now, is it even native code? That becomes a very hard argument to make when you're trying to advocate these things. So I'm going to look at a particular EDSL that I did not write. This is from Connell Elliott. He wrote Pan. He was designing an EDSL for generating images. And his big insight was to say that an image is not a collection of pixels. It is instead a function from pixel coordinates to a color. And turning things around in this way has some great side effects. Your scale invariant. You can blow up an image. You can shrink down an image. You can, most importantly now, you can transform an image by transforming a function. So this gives you a way of composing diagrams out of smaller pieces. So we are going to be using an EDSL. And this is going to be using an EDSL framework that I am developing. You're going to see things like this repr, which is a representation. I sometimes call it E for expression. And that's indicating the language that I'm writing in. It's going to be a variable always, because we never know what language we write in. But what we're going to do is, depending on the program we write, we're going to put constraints on this language. And those constraints are going to be an enumeration of features that we want. So for creating images, we're going to want arithmetic. We're going to want trigonometric functions. We're going to want some image accessing things, or maybe array accessing, just so we can do the output rendering at the end of the day. But you can see the core of Pan here. So we have two-dimensional points. An image is a function from points to a color. A color image is a function from points to a color, which is 4 floats. So if you're a game programmer, this is getting a little bit worrying, I'm sure. And transformations are just functions from points to points. This works out really nicely. Translation is just a function from points, so we can just add an offset, and that, there we go, we've translated it. Scaling a point, this is going to be a point-wise multiplication. It's just multiplication. So our EDSL is really neat. Now, those pluses and times, those are loaded, right? These are not innocent bystanders. We can build up images. We can interpolate colors. We can interpolate entire images. There's some ASCII nonsense in there. So again, for the non-Haskeller, you might be a bit off-put. But I hope that the plus and the times look pretty reasonable as definitions. The other ones, there's basic arithmetic happening here. So let's get started. So Connell in his paper defined dozens of figures, and all I did was I translated them to my EDSL as I was building it as a test to make sure that everything worked for me. What I wanted to do is compile it to Opencl. Opencl is an open compute language. It is designed to make it easier for you to program embarrassingly parallel problems, so things where you could have a whole bunch of independent threads, and it's primarily targeting systems that have very wide SIMD vector units. So something that could take 32 floats and add them to 32 other floats. And how is that useful? Well, if you have a whole bunch of pixels that are notionally independent, I could just sort of unroll the loop 32 times and compute for all those pixels at once. As long as the computation that's needed to compute every pixel doesn't diverge, then everything goes perfectly smoothly. The headache comes from when they do diverge. Thankfully, the Opencl compiler and runtime engines have ways of dealing with that. So I want to compile all this to Opencl because it's very portable. It runs on CPUs, it runs on GPUs, Mac, Windows, Linux. And we get some code. It is not the prettiest code, but again, it's readable. Yeah. So this is generating. It says get my global IDs. This is going to be my thread ID. Get the image size, and then do that trigonometric stuff for this sort of ringing function that we're defining, and then we write it out. You can see all the consts, so the code generator is very particular about wanting things to be const. Good for it. And we can then see it compares rather favorably, and when we run it, we get a picture. So, super beginnings to the pan examples, and they take off very quickly. We can add colors. So we have rings, and we have a blue image, and we have a yellow image, and then we use the rings to interpolate between blue and yellow, and we have blue rings and yellow rings. I opened off the talk with that sort of spirally looking thing, which is very complicated. And this is the program that generates it, Fig22. This looks kind of frightening, but we're going to run it through the code generator. Again, the code generator takes this and gives you a Haskell function. And it's a mouthful. It's not interesting, which is exactly what we want, though. It does some destructuring of vectors. It does arithmetic. It does a lot of common subexpression elimination. The consts are our notion of purity here. So there's about a dozen optimization steps that are happening. This language that's used for all of it is composed out of about 20 language features, such as branching and arithmetic and trig functions and arrays and so on and so forth. So that's the code that we write, where it says we are going to have a disk, and we're going to crop that yellow-blue rings to the disk, so we have a sort of center part. Then we're going to do a radial ripple that's going to have a kind of spider web shape to it, and we are then going to swirl the whole thing, and we end up with that beautiful picture. So that is really nice, but this is a toy, right? And I came dressed for speed, and so I'd like to know what's happening here. So we, even in a little laptop like this, this is the low-end MacBook Air with 2 cores, we can run the Haskell backend. So generating a 1024 by 1024 image, 4-channel float colors, and it runs at 5 hertz. I don't know if this is good or bad. This is about a 720p kind of resolution. You don't normally run a game like that and doing a lot of trig functions. I suspect it's not bad, but we have a lot of options. We could run on 2 cores. So running on 2 cores presents a rather nice benefit. They also have hyperthreading. So we're not going to change any code, right? We're just running Fig22. These are all just GHC RTS options. So we can run with 4 cores. Now we're running at 20 hertz. It's now a 1024 by 1024 image with 4 channels of float color at 20 hertz. That's sounding pretty good, but nobody does software rendering anymore, right? Well, maybe they should, because what if they could use Opencl? So OpenCL I mentioned, these are compilers written by Intel, by Apple. They know this CPU really well. They're going to take advantage of the SIMD hardware. So this is GHC running our FIG22 definition as best as it can. GHC doesn't know a whole ton about SIMD operations. It's running through the LLVM backend, which knows a little bit, but let's cut it some slack. How is it going to compare to OpenCL that's running and knows everything? We have SIMD vectors. Let's hope for if everything went well, it would be like a 2 to 4 speed up. And it is exactly a 2 to 4 speed up. So now this is now running on OpenCL on the CPU. And of course, let's change the C to a G and run on the GPU. So the value here is not the fact that now we're rendering our pan images at a rate that's probably higher than we need. The value of this is the existence of this spectrum. We made one definition for a functional definition of an image, and we run it on 1 core, 2 core, 4 cores. We run it through an OpenCL backend if that's available for the platform we're running on. Or we run it on the GPU if that's a platform that we're running on. And the performance scaling is exactly where we expect it to be, right? So the scaling on cores, we got better than linear going to 2 cores, which isn't super shocking because it is very, very easily parallelizable. Going from OpenCL to GHC, that gap is smaller than I thought it would be. I thought OpenCL would beat GHC by 4 to 8x. So all the credit in the world to the people writing the backends for GHC. And then the GPU on this guy is an integrated thing, doesn't have its own memory. It's got something like 12 execution units that have like 64 wide SIMD vector units. But it's another factor of 10. So this is great. These are choices. So now when you're figuring out what platform do I run on, you have a lot of options. It's not go big or go home. It's go anywhere in between and whatever meets your needs. And the same software that you wrote will get you there. So that's Connell's work with pan. The natural question with 2D images is, what about 3D? Do we want to say that I'm going to have a function that takes a 3D point and gives you a color? That turns out to not really be what you want to do. It's hard to sample 3D space. So instead, we're going to do something a little bit different. And we're going to say, give me a 3D point, an E with a V3A, and I'm going to give you an EA. So here A is the scalar of the vector field. And this is just going to give you a distance. So we're going to use distance functions. So now all of our solids are going to be made out of functions. So a sphere takes a point. The sphere is by default centered at the origin. And you say, how far is this point from the surface of the sphere? And I just have to subtract the radius off. So that's the real code. This is a signed distance function. So if you're inside the sphere, you get a negative value. If you're outside, you get a positive value. And you can imagine now, what can I do with this? Well, I can render it, right? I can shoot out a bunch of rays. And when they hit something, I just have to figure out what color to draw on the screen. But these representations are continuous. So again, we have the scale and variance. We have the ability to transform our definitions and manipulate them programmatically. So let's look at some more of these distance functions. These are unsigned. It's easier to do it that way. A box and a box with rounded corners. Again, even if you don't know Haskell, I think the code looks okay. I got this from Inigo Quiles, who is a brilliant graphics programmer. And he has a website where he has tons of cool graphics tricks. And he has a bunch of OpenGL shader programs that implement these things. So I could take a shader program and type it into the Haskell program. And they look a little bit different, perhaps. But mine's much more polymorphic, for instance. Like if you get some hardware that could work with doubles, you're in luck. If you get some hardware that works with some sort of truncated float representation, losing precision, no problem. Same code is going to work. So I decided to build a scene. This looks rather complicated. But the idea was to have a sort of pedestal like this desk, I guess. And then I was going to take a rectangle, a block, and sink it into the pedestal. And I was going to use a tunnel, which is a cylinder that's sliding through that block, but that's being subtracted. So I'm going to get a tunnel through the block that's on top of the pedestal. I take that and I run it, and we get this that runs at 60 hertz on this laptop again. So this is now doing a little bit more work because I also have a light source that's floating around in some strange way. We have soft shadowing because the ray marching can say, well, this ray got to the point, but it came very close to hitting some geometry because we have all these distance functions. And so we can get nice soft shadowing. So this is a very composable way of getting 3D geometry to which you can apply quite attractive lighting models. And it runs very, very fast. And it's happening because it's spitting out some gargantuan amount of OpenCL code from about 10 lines of Haskell. Okay, what does this have to do with robots? Now we're going to get into work that is extremely current and is not finished by any means, but I had to do this. So this language construction framework is, of course, quite easily adaptable. Take away the features for accessing images. GPUs are good at images, but something with 2 kilobytes of RAM is not. We don't want any dynamic allocation. Maybe we want to take away the ability to do branches. We don't want geometric functions on vectors. We want basic arithmetic, and I want to be able to read from arrays. So I want to pull out those language features, and I'm going to want to add in a few more, because the way that we're going to program microcontrollers is we'll follow a Arduino type style, where you have really just a loop that's running. The loop reads from some sensors, and then it's going to output some value. So the story behind this is that Gershom asked me to give a talk here because he assumed I would have flying robots. So I said, of course. And because I'm an academic and somebody says, do you want to give a talk? You say yes. And this was really tricky because I don't have anything to do with flying robots. But I was comfortable in the lie. So after Christmas, I said, well, what does it take to get a UAV going in your house? And it's surprisingly not expensive. Mine was $20 because I shipped mine from the US because this was just a couple weeks ago and we're a tight timetable. As well as a small price, these things are amazing. Look at this. This thing has an accelerometer in it. So an accelerometer is giving you a down vector so it can maintain level flight. It has a rate gyroscope so that it knows how it's turning. So if it's turning about an axis, you can put a set point in and say rudder left and it'll turn left using its gyro, okay? It's got these 4 motors that are counter-rotating to not exert sort of a constant torque on the whole thing. This is wonderful, but I am really terrible at soldering, so that was going to be a problem. And people still have not reverse engineered the protocol used by the transmitter. This is really frustrating. There are people who are very passionate about reverse engineering remote control toy transmitters. And they're brilliant people with very steady hands. But they keep on making new production runs of this using different components, because they're saving money, I suppose, and the protocol changes, so nobody knows how to talk to it. So this is the controller you get. It has 2 joysticks, and it works quite well. I can almost fly this thing, which is really a testament. But there's just no software SDK. There is no API. As a roboticist, though, there's always an SDK, right? And it looks hard, but it's quite soft. So this is an Arduino Pro Mini. This is the system that has the 2 kilobytes of RAM that I mentioned. And I'm going to write code for it, and I am, come hell or high water, going to get it to talk to the transmitter at the very least. I can't put it on the quad rotor because it will fall. It can't carry anything. It's so tiny. So this is what the code looks like. So this is an example program where I want to get 2 things from downstream. I'm going to sum them, and I'm going to yield them upstream, because this is kind of the structure of what an Arduino loop looks like. So as I mentioned, this is work that's in progress and not done. The way that I do these code generators is I think of a language feature that I want to add, and I do a back and forth of writing code manually and writing the Haskell code I want to write, and make sure that I can meet in the middle. So I tend to glue them piece to piece. And so this is generated code for that. It's not done. There's a magic part in there. But it essentially pulls a trampoline out of a composition of iteratees or pipes or machines that you might be familiar with. So a warning, as I mentioned, this work is not done, but I needed to have some flying vehicles. I didn't have a nice joystick, so I used my keyboard, which is a terrible way of flying a vehicle because you can just go a little bit more, a little bit less. You can't fly. But I did try. So you can see. Research lab at home. And this is pairing the transmitter. It's plugged in via USB to the laptop. I apologize for that. To the quad rotor. You have to execute certain commands to get there. I put it into a calibration mode so that the accelerometers can be zeroed out so it can fly real smoothly. There's calibration mode, so I'm being very careful. So that was a crash. So that was a full battery charge on a nano quadrotor that you can buy yourself, and I highly recommend it because they are tremendous fun. Okay, so we've learned things about Haskell, things that are true and things that are not true. It's very flexible. It protects you and it enables you. In terms of wardrobe, the types are sort of Batman's utility belt around your values, right? They're not just there to protect it, they're to enable it. You can pull it onto a GPU, pull it on a CPU, different cores, blah, 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 all that great stuff. EDSLs do not have to have any overhead at all. So if you want to simulate and you run it, and it runs at the pace you want it to, you expect it to run at. And there are no systems too big or too small. You might say, I wasn't really writing Haskell, I was writing C, but whatever. If I write in C, I'm not writing in assembly. This is what compilers are. We're computer scientists, we're programmers. We should be familiar and comfortable with working at different levels of a system. And that is everything. Thank you.